I sent it to you last night. I think there were some people didn't get their full mark because of the following. Let me try to explain. What if you have something like this? Right? If you have something like this, guys, okay, it's not, I mean, because these two have the, I know g of tx approaches 1 as t goes to infinity, and so is gt. So both of them approach the same limit, but that's not an argument. I mean, it's not a, I mean, the fact they both approach the same limit doesn't mean that this, I mean, you can say that this is not, I mean this is, if you, I mean, it's okay to say this, but if you say this is equal to this, it's not, I would consider this as not detailed enough. I mean, not justified. I would consider this as not justified enough, right? Because you're saying that both of them go to this, because both these go to the same limit, that this must is I mean, it's mathematically speaking, it's not justified. I mean, it may be correct mathematically, but this, I mean, as you know, in mathematics, you have to justify every single step. So saying that this is equal to this, although it may be correct, is not justified enough, right? I think the way to do that, or one way to do that, is as follows: is to write this as, I mean, there are several ways you can do this. One way is to write this as lim okay, as t goes to infinity, and then you can apply the one of the rules I mentioned to you earlier, which is alright, then the 1 and the 1 cancels, right? And the a cancels, and this becomes the limit of 1 minus gtx divided by 1 minus gt. Alright, so this is a proper justified argument, right? Okay, because we are using the result. This is a proper justification that this is equal to this, right? That this, right? And in this step here, I've used the argument that as z approaches 0, right? So this is the result I have used. Okay. You follow me what I've done. I know some of you try to argue that because these two guys approach 1, right? This must be this. Doesn't although it makes sense, it doesn't. That mathematically, it's not rigorous enough. I mean, it's not. I mean, in mathematically, it's saying that this is equal to this, without any justification, is not rigorous enough, right? The argument that these two approach the same doesn't imply immediately that this is equal to this, right? You have to really. I mean, a lot of things in mathematics are obvious, but you have to make the effort to prove it rigorously, you know? Yeah. Okay, you know what I'm saying, guys. So, another way to prove it is as follows. I mean, this is only one way of. Can you see this, guys? This is one way of showing it. Another way of showing that this is equal to this, right, is to use the L'Hopital's rule. So if you use the L'Hopital's rule, then you can write this as as t goes to infinity. Now as t goes to infinity, you know that, where's my red pen? I'm trying to find my pen. Oh, I can't find it. Anyway, so the a and the a cancel, so this will become, and this guy here, because as t goes to infinity, this goes to 1, and so is this one. Okay, so this will become the limit as t goes to infinity of x gt x divided by gt. Okay, and then again by the L'Hopital's rule, but it's in the reverse direction, right? You can write this as the limit as t goes to infinity okay. So this is another way of showing that the limit on the top is the same as the limit in the bottom, right? Just using the L'Hopital's rule. Is that clear, guys? Okay. Okay. So anything. I mean, you have to be rigorous. I mean, rigor is important in mathematics. So you have to be. You can't just argue that because these two have the same limit, this must be the same as this. Doesn't. I mean, although it may be correct, it doesn't have the rigor, right? Okay. Okay. All right. So that's the comment about quiz 3. Do you have any other questions? Yeah. Any questions you guys have about quiz 3? Are you still satisfied or not? Hello, guys. Are you still satisfied? Yes. And I know some of you. You okay? Okay. All right. So do you? I mean, and as I said, like you can't just say something. I mean, everything in mathematics has to be precise, right? It has to be precise. You know, you can't just say because something and something has the same limit, so this must be true. It doesn't follow. It doesn't follow that way. Okay. Okay. All right, guys. All right. Now let me go back to the what we did yesterday. Unless you have still want to talk to me about quiz 3. Let me go back to what we did yesterday. We started talking about financial risk measures, right? So a financial risk measure is, all right, okay, first of all, a financial risk is a loss associated with the investment. And a financial risk measure are the probabilities associated with the risk, right? So then I showed you two pictures, two funny pictures. So these are the pictures I showed you yesterday. This is a loss. What? This is a risk, right? Risk. This is a picture of another risk, right? Two risks. So pictures of two risks. All right. Then I defined what I meant by a risk measure. So a risk measure must satisfy three properties, known as the normalized property, the translated property, and the monotony property. Right? This, and this. Right. So this, okay. And then there is something known as a coherent risk measure. Coherent, loosely speaking, means is a intelligible or good risk measure, right? So that measure should satisfy 5 properties: the normalized property, the translated property, the monotony property, the positive homogeneity property, and the subadditivity property, right? Okay. Then I talked about the two most popular risk measures. The first one is VAR, right? And the second one is known as expected shortfall. This is the second most popular risk measure, right? Okay, so and then I asked the question that are VAR and ES coherent risk measures. The answer was that VAR is not a coherent risk measure because it doesn't satisfy subadditivity, but ES is a coherent risk measure, right? The proof, you should look online. I'll send you a link later on today or maybe tomorrow. There are like half a dozen proofs showing why VAR is not a subadditive risk measure. So if you look online, you will find at least 6 different proofs based on 6 different concepts, right? But I'll try to send you them later today if I can find. Okay. And then I showed you some newspaper clippings. So these are articles blaming VAR for the financial crisis that occurred in 2008. So they argue that VAR, because it's not a coherent risk measure, could have played a role in the financial crisis in 2008. So this is one article. This is the second article. The third article. This is the fourth article. Okay. And then, what did I do later? Then I provided simpler expressions for VAR and ES. So if X is absolute, is a continuous random variable, then the expressions for var and es can be simplified to this and this, respectively. Okay. Then I did 3 examples. So this is example 1 for the normal distribution. So the formula for var is given by this. Okay. Now you may find, and one of you asked me yesterday after the class, that why on the right hand side there is no x, because var is a measure. It's like, for example, if you're taking an expectation of a random variable, what you have on the right hand side doesn't depend on x, right? Okay, so expectation of x, if x is a normal variable, the expectation of x is mu, and mu is a constant, it's not a random variable. Okay, all right. So, and this is the formula for the expected shortfall for the normal random variable, right? And this is example 2 where x is assumed to be uniform, and this is the formula for var, and this is the formula for es, right? And example 3, x follows the exponential distribution. This is the formula for var, and this is the formula for es, the expected shortfall. Okay, guys. Right, and finally, I did this yesterday. I wanted to prove the 4 properties that value at risk satisfies. Okay, so I proved the first one, and I asked you to think about how to prove the second one. Did you guys have time? Yes? No? Come on, guys. You didn't have time? Alright, before I go further, let me give you quiz number 4. Are you okay with this one? Quiz 4 is due on the 19th of February. This one brings the text. Hello, sir. How are you? Are you guys okay? Are you okay with the quiz 3 now? The problem? You understand? Are you guys okay? This is quiz number 4. Quiz number 4. Are you there? Okay. You guys okay? All right, guys. So quiz 4 is due on the 19th of this month, and next Tuesday, this time we will have a test in this room. So from 4 o'clock to 4:40 p.m. next Tuesday, we will have a test. And if you look at the email I sent you, it explains everything you need to know. You guys read my emails, guys. All right, okay. Let's see how we can prove this. This, if you assume that x is a continuous variable, right? This guy here is equal to right? Okay, guys. Now, okay. Now, can somebody tell me what this is equal to? What would this be equal to? Hmm? F, the inverse function of f, of p, equal to p, yeah? Okay. All right. All right, guys. So you see what I've done. I have assumed the result, and I have shown that after a few calculations, p is equal to p, which is always true, right? Okay, and therefore the property must be true. Okay, is that clear, guys? Or not? Yeah. Okay, so that's how you prove the translative property. The next one. The next property is what? Is the monotonic property, right? Is it number 3? Is it monotonic? Yes, the monotonic property. M-O-N-O. Okay. Now, the monotonic property says that if x is less than or equal to y, then the corresponding rest measure must also satisfy the same inequality, right? But if x is less than or equal to y, it means Okay, so if two random variables are ordered like x less than equal to y, then corresponding quantile, I mean these are known as the quantile functions or the inverse CDFs, must also satisfy the same ordering. Okay. Okay, that's number 3. Number 4. Okay, is the positive homogeneity property, right? So we need to prove that. Do you guys remember the positive homogeneity property, which says that we did it a long time ago? It's this one here. This is the positive homogeneity property, right? Which says that rho of c times x must be equal to c times rho of x. Okay, this is alright. This is the okay. So this is the same as saying that the var okay. Okay, so okay. Now this thing here is simply P. Now this guy here, you can write it as the probability that Cx is less than or equal to C times okay. The two C's cancel out, so you get this, right? Okay, and this becomes all right, P equal to P, which is always true. Okay, so hence the property holds. Okay. All right. Any questions on this, guys? Are you okay? So we have proved the first four properties of var. The last property, which is subadditivity, is not satisfied. All right, and I will send you later today or tomorrow. I will send you a proof of the fact that var does not satisfy subadditivity property. It's not an easy proof, so I will send it to you. I will send you the link if you want to look at it. I mean, it's not exact. I'm not going to examine it. I just want to show you that why it doesn't. I just want to show you why var does not satisfy the subadditivity property. Right? I will not ask you in the exam to prove it. Okay. All right, guys. All right. All right. The next thing I'm going to talk about. So far we talked about. All right. The next thing is the next thing I'm going to talk about is estimation. I mean, so far we only talked about formulas for var and formulas for ES, right? But we haven't talked about anything about how to estimate these formulas in practice, because in practice you have data on losses. Every company in the world has a data set on losses, and they want to know how to estimate var and how to estimate expected shortfall, right? Okay, so the next topic I'm going to talk about is estimation of var. Right, and there are three different methods I will talk about. The first method is parametric estimation methods. So when I say parametric estimation methods, what they mean is that they assume that the data and the losses come from a specific distribution, like the normal distribution or the uniform distribution or the exponential and so on. The next one I will talk about is the non-parametric estimation methods, and the third one I will talk about. Non-parametric means, have you guys done non-parametric methods before? I mean, anyway, if you've done or not, non-parametric means that you don't assume that the data come from a specific distribution. So the estimates do not assume any specific distribution for the data, right? The third one is semi-parametric or semi-parametric. Estimation methods. So these are three sets of methods I will talk about, not today, but I will start talking about the first one today, right? And then we will see how far we get. The first one is A. Okay, parametric estimation method. So the first, I'm going to assume the first parametric estimation method. I'm going to assume that the data and the losses come from a normal distribution with parameters mu and sigma squared. So we know that this is the formula for var, right? We did this yesterday, right? I assume all of you know what MLE is, right? Do you guys know? I'm sure MLE is maximum likelihood estimator, right? Short for maximum likelihood estimate. If you don't know it, we'll write it down. Maximum likelihood estimator. Okay, it's MLE. Yes, I should say. Right, where now if you done statistical methods last year, I know some of you did that course, yeah, last year, you would know what the MLE for mu is. What's the MLE for mu? You forgot, man.
X bar.
X bar, of course. Just kidding. Just testing your memory now. Okay. And the MLE for sigma is 1 over n okay. So again, I mean, if you haven't done my course last year, you can if you go to the website, there's a link to statistical methods which I taught 2 years ago. So you can find the details about how to derive these. You can actually prove that the MLE for mu is x bar, the MLE for sigma is this guy here, right? So this formula here gives you the estimator for value at risk. So if you have a data set on losses, you can use that formula to estimate the value at risk. So it will give you a number at the, okay. All right. Now, before I go further, I'd like to introduce you to something. This again comes from this is a reminder from Statistical Mothers, which you have or you have not done it. Okay. Suppose okay, suppose you have theta hat is an estimator of theta based on the sample of size n, right? Okay. There's something known as, I'm sure you've done this before. I mean, if you haven't done it, just look it up in my website. The estimator is said to be unbiased if the bias, which is defined as the difference of expectation of theta hat minus theta, is 0, right? Okay. Theta hat is said to be asymptotically unbiased if the limit of the bias as n goes to infinity is 0. And finally, an estimator is said to be consistent, right? These are terms you should have learned earlier. If the limit of the MSC is 0 as n goes to infinity, where the MSC, I will define what MSC is. MSC stands for the mean squared error and is defined as the expectation of Okay, and this term here, MSC, means the following. It means mean squared error. Okay. So these are things. I mean, I'm just reminding you of these things because these are stuff you should have learned before, right? But if you did not learn this stuff, just make sure you know. Make sure you know this stuff, right? So these are stuff. Let me put them in a box so that you know what I'm saying. These are stuff you should have learned before. I'm assuming you know this. If you don't know this stuff, you can look it up. You should look in my website for the notes for statistical methods. It contains a lot of examples on this. Right, so this is from Math 208. Is it? What's the code for statistical methods? 20812, right? Or 2? Huh? You can't remember? I think it's 12. Maybe, I don't know. I may be wrong. You can check online. You guessed it a long time ago. I mean, if so, these are stuff you should know anyway. Okay. So I'll put it here. Now going back to the normal distribution method, it can be shown that right, it can be shown. I'm not going to do it because I will not ask you this in the exam. Well, if I ask you this in the exam, I will give you enough hint so that you can do it. It can be shown that the estimate for VAR is asymptotically unbiased and consistent. So it means that the bias approaches 0 as n goes to infinity, and the MSC also approaches 0 as n goes to infinity. So you can try to do this yourself, but if you have problems, come and see me. Right? If you have problems proving either of these two statements, come and see me, okay? Next one, number 2. Oh, you look tired. What's the problem? All right. Okay. This is back to. By the way, I should have said here. This stuff here is also from. Let me put a box here, guys. You may wonder where this result came from. So if I put a box here. You will know where it came from. Okay, this is from okay, this is from Statistical Mothers. All right, now can you, my friend, can you tell me what's the MLE for this is? Hmm? You should remember from last year. Come on. Right. So this is the MLA for, once again, this result. If you don't know where it comes from, if you don't know where this comes from, just please look up did you do this last year, guys? How to show that the MLE for the uniform distribution? You did? You don't remember? Okay. Anyway, if you look at my notes, you will see, right? And again, the right, that's number 2. Okay, number 3 is the exponential distribution, which we did yesterday, you may recall.